Welcome everybody to PyCon 2026. This session will be about free-threaded Python by Thomas Wouters. And it's about the free-threaded Python project, how it's going to help us and why it's a smooth transition. And let's welcome our speaker very warmly. Thank you.
Thank you. So for those of you who don't know me, and I know that's not the people in the front, my name is Thomas Wouters. I'm a long-time CPython core developer, which means I work on the CPython implementation of Python, which is the one most people are using. And I've been doing that for the last 25 years. Also relevant to this talk, I'm on the steering council. I've been on the steering council for 5 of the last 6 years, which means I get to decide on things like this. And I work at Meta, where I work on free-threaded Python, among other things. Come visit us at our booth. We can talk about free-threaded Python. We can talk about Cinder, which is our Python implementation, and JIT. We can talk about Firefly, which is our type checker written in Rust. And we can talk about lazy imports, which is one of the cool new features coming in 3.15 that we worked on. And also, not quite relevant to this talk, I have cats. I have great cats. I have such good cats. In an alternate universe, there's a version of this talk where I just use my cats to as my slides. Like, I have so many cat pictures that I can use, and they are relevant, like so relevant. That's not this talk, though. This is a boring talk. This is a boring talk about free-threaded Python, which is the effort to remove the global interpreter lock from CPython to give us real threads. And for people who can't see, yes, I am doing scare quotes. So you probably know what threads are, but I'll just go over it. They are a separate thread of control in a process where you can have multiple things execute within the same address space. And their primary reason really is performance. It's because memory access is slower than CPUs. CPUs are often waiting for memory, so why not give the CPU something else to execute in the meantime? You can do the same thing with processes, but processes have their own overhead, and they have their own memory space. So it's not as easy to just drop in processes. For Python and things like Python, there are good reasons to support threads besides performance, which is blocking APIs, where you can just call a blocking API in a thread while your main program continues to do its normal thing, or vice versa. Or if you need to interact with a third-party library that requires that you use threads for its access, like common in databases. The global interpreter lock is how CPython decided to support threads more than 25 years ago. So I was not part of that. But I will say, it protects Python objects. It protects the reference count, which is how we track whether objects are still being used. It protects a lot of the CPython internals. And it is very efficient. It is the most efficient way that CPython can support threads. The GIL does not protect your Python code because you have no control over when Python releases and then reacquires the GIL. It mostly does not protect your C++ extensions either, or C extensions. You have a little more control there. You can know when you call things that might release the GIL, but it's still very easy to unintentionally rely on the GIL and end up not being safe. And fundamentally, threads are hard. They are a complicated thing. The GIL does not make them any easier, even though sometimes it does seem like it makes them easier. So why do we want to remove the GIL at all? Fundamentally, the GIL makes threads less useful. It removes the main reason for threads, which is performance. Multi-core hardware nowadays is everywhere. Like, my phone has like 8 cores. Back when Python started, 2 CPU systems were extremely rare. When it got the GIL, they were not any more common. So the answer has been, for many years, rewrite it in C. The last couple of years, it's been rewrite it in Rust, which I agree is better, but it doesn't always fit. It means you have to rewrite most of your application because not only do you need the code to be not Python, you need the data to not be Python. So that answer doesn't always fit. We do have some alternatives for specific use cases. Multiprocessing is a very common one, that is using processes as if they're threads, automatically copying data back and forth. It uses a lot more memory. There's a lot of copying going on. It's not always suitable. Subinterpreters are fairly new. You can have multiple interpreters in the same process that each have their own GIL and can be run by different threads. The interaction with third-party libraries, especially libraries not aware of Python, isn't there yet. There's no good way of copying data yet, so it doesn't always address the use cases either. And then async IO is a very common one. That's basically green threads. I'm a big proponent of async IO. I think it's the best way of dealing with network IO, where threads can easily lead you wrong, but it doesn't give you the performance you need. It's still one thread of control. Without the GIL, multi-threaded solutions to those things can offer higher throughput, lower memory use, and lower latency. So I mentioned threads are hard. Threads are hard because sharing data is complicated. And CPUs and compilers optimize for speed. Because memory access is so much slower, they end up caching data, they end up prefetching data, they end up reordering memory accesses as they see fit. And that interaction with threads is extremely complicated. When one thread is writing to a piece of data, does another thread executing on another core see that new piece of data or not? Do they see half of the new piece of data? If you write to two things in one thread, which order does the other thread see those in at all, right? Maybe not. So the rules for these things are complicated, and they involve things like memory fences, atomic operations, a memory model. Those are big, scary words and complicated subjects that I'm not really going to cover. I'm just going to say shared mutable data in threads is bad. Now, the problem is in Python, everything is an object, and everything is shared. The way the Python object model works is we don't have variables that are memory. We just have variables that refer to objects, which are memory. And those objects can be referred to by any thread. We use reference counting to track which objects are still being used. That's a little bit of data inside every object that is mutable. So everything is shared mutable data. We also have the problem that the CPython C API relies on the GIL in multiple ways. For instance, the pydict getItem call returns a borrowed reference to a value in a dict. That's not a problem if you have the GIL to make sure that the dict can't be changed while you do something with that reference, even if it is just increasing the reference count so you have your own reference. But if you don't have the GIL, then that dict can be changed, technically be changed at any time. Even in practice, it probably won't happen. But it means we do rely on the GIL for correctness. And the Python types, the dicts, the lists, tuples, code objects, function objects, they're everywhere. The whole process is full of these. Their performance is really important. So if we want to replace reference counting with a lock, that's extremely expensive. If we want to replace pydict getItem with something that uses a lock, that's also really expensive. And that affects all Python code, even if they don't use threads. And there's a lot of code out there. There's a lot of Python code. There's a lot of extension modules as well. And we could work towards removing the GIL by changing the semantics, by changing the C API. That's a lot of work, and that's going to affect a lot of code. And in the meantime, the performance still matters. We can't slow down the interpreter by 50% in order to support making multiple threads executing at the same time that much faster if nobody's out there is using that many threads right now, because they can't. So there have been multiple attempts in the past to remove the GIL. I mean, the original patch by Greg Stein was in 1995 or 1996. It replaced reference counting with a fine-grained lock and a bunch of other things in CPython with fine-grained locks. That was not successful because it was just too slow. The performance, it showed us a very significant performance penalty, and threads weren't that popular at the time, it was not something that was acceptable. Trent Nelson started something called PyParallel in 2013. That was a completely different model, where it did use platform threads, but from Python you would use a completely different API, where you would spawn off a bunch of threads to do something, and then the main thread would wait. And it would defer a lot of the operations, like memory collection and reference counting, until all the threads were done. That didn't work because people want threads the way the other libraries are using them. And it wouldn't work with anything that was already using threads, right? And then in 2015, Larry Hastings started Galectomy. He worked for a couple of years on novel approaches of dealing specifically with the ref counts, but also recognizing these other problems in CPython and the things we would need to do to actually remove the GIL. And in the end, he pretty much gave up. I mean, he wanted to explore some other areas, but he didn't get around to it. And then a couple of years ago, Sam Gross, who works at Meta, thought he could solve most of those problems, and he did so in a fork of Python called no-GIL Python, fork of 3.9, to make it all work. And that's what we have now, more or less. Sam wrote PEP 703. He described all kinds of things, all kinds of different techniques needed to support free-threaded Python to remove the GIL. For example, now in free-threaded Python, objects have a thread owner, like a thread that is the owner of the object. That doesn't mean the thread is responsible for the object. It means that thread gets to have fast access to the object, to the ref count, and to anything in the object. Other threads can still access the object. They need to use a slower path, which is a separate shared ref count. And using atomic operations for that, but using the fast operations in the main thread, or not main thread, in the owning thread, means you can prioritize and optimize for the common case of a thread doing a bunch of things with an object. We also defer a bunch of ref counts. Now this does mean some semantic changes, because this means we're not doing ref operations now. We're going to wait until GC, and then we're going to consolidate a bunch of operations and do them at once. This means that objects that got destroyed immediately because of ref count operations now get destroyed when GC happens, but it's a small difference, right? It's probably acceptable. We also do speculative ref count operations, where we get an object from a dict, for instance, and then increase the reference count, because that's what you need to do. And then we look if the object is actually still in the dict. This sounds really weird, and it sounds like that's dangerous because the object may have been destroyed. But there are safeguards in place, so we do this safely and in controlled circumstances. It's not something that other people should be doing. This is magic in the interpreter itself. And then there's quiescent state-based reclamation, which is where memory, for instance, the memory used by a list, is not freed when the list is reallocated. Instead, the old memory is kept around so that other threads that haven't seen the reallocation yet get to use that old memory safely. And we clear that memory when GC happens. Or rather, when we know it's safe to do so because all threads have caught up, which is typically when GC happens. There's also a bunch of fine-grained locks because you can't really get around it. Some things just need a lock. And then to do all this, we also need a new garbage collector because the old one was complicated to make threads safe. So as I mentioned, threads objects have an owning thread. We have a new special thread-aware memory allocator called memalloc, which is very optimized for threads. Also gives us the way to access potentially invalid objects safely. And that's really important. And it also has hooks that we can use to implement quiescent state-based reclamation. Using all those together, we have lock-free dicts, where especially for the owning thread, access is really fast, but also for other threads, access is pretty fast. Same for lists, same for other important types. We still need a way to stop all threads from executing or changing state when we want to do things like change the type of an object. It's really hard to figure out which threads we would need to notify about changing the type of an arbitrary object. So instead, we wait until all threads are blocked. We stop the world, then we make the changes, and then we run them all again. We also have per object locks called critical sections. They're not normal locks. They're a special type of lock that's deadlock free. Now, if you've ever worked with locks, that sounds like an oxymoron. It works in Python, in CPython specifically, because we recreate the semantics of the global interpreter lock in the critical section. So in the part where the critical section lock is held, when we make a call that would otherwise have released the GIL, it may release the critical section, and then it is reacquired before execution continues. So this is really great for emulating the effect of the GIL on C or C++ code in a specific block of code. It's not really a replacement for locks in general. And all of this together means that, and then in order to do both the critical sections and the stop the world, we repurpose the existing calls to acquire the GIL, which is a whole bunch of different calls like pygil state ensure. We repurpose them for a thread attach and release because we still want to know when a thread makes a call to something that, for instance, a system call that blocks. We don't want to wait on that thread when we stop the world because it might be blocked forever. So instead, we use the GIL acquire and release calls to track which threads are actively using Python and which ones are off doing their own thing. And stop the worlds and critical sections, et cetera, use that to make sure to wait for the correct threads. And all of that together means in free-threaded Python, thread semantics are almost the same as in GILful Python. We don't have a memory model. We don't have the scary memory model atomics, memory order issues. We don't have memory fences. None of that is important. Python just behaves like Python. So this is where we are now. In Python 3.13, we added free-threaded Python. And I will say, free-threaded Python is not the name that Sam chose. This is the name that the steering council chose because we didn't like no GIL having a negative because then we'd be talking about a no GIL build. So free threading is not an industry term. It's not something that means anything other than specifically in the Python case, it means getting rid of the GIL. And I say that because free threading in Python is much less free than threading is in most cases. Like in C and C++, you can go bananas. You can write all over your memory if you want. In Rust, it's a little better, but it's a lot more free than it is with free threading. So in 3.13, we added experimental free threading support. It's relatively slow. It's like 20 to 40% slowdown on single-threaded workloads. And there are some thread safety issues. There are some scalability issues where using more threads make things go slower. But it does work. It proved that it worked. In 3.14, we made it much safer. We made it much faster. There's a 0 to 10% slowdown. I'm still personally shocked that we got to 0% slowdown. That's on ARM hardware. There's some magic going on there. I don't know what it is, but it's amazing. On Linux, with GCC, with Clang, it's usually around 5%, sometimes 10%. On really old compilers that don't really understand the complex logic involved, it can go a little slower, but use newer compilers. So in 3.14, I was not on the steering council. I managed to convince the steering council it was a good idea to declare free threading supported, like an official supported thing. This was originally the plan as well. It just required a lot of making sure that we ticked all the boxes. And then this year, 3.15 will be released, and it will contain a single stable ABI for free threading and GIL builds, which means you can build extension modules once that will load into 3.15 or later using either free threading or a GIL build. So we also included a bunch of scalability improvements, by the way, but those are less noticeable. That's just, if you use a lot of threads, you'll see some improvements. So the way to add support for free threading to your C extensions, that's the daunting bit, right? There's all these changes. How are you going to deal with it? Well, Quansight wrote a really good guide, pyfreethreading.github.io, that includes a guide for porting your extension modules. And it's not that hard. You need to protect your C globals because you're no longer protected by the GIL. But like I said, maybe you weren't already. You can also just get rid of your C globals. That's not a bad idea. You can use critical sections to protect mutable instance data on your objects. If you want maximum performance, like if you want a lot of threads to access your objects at the same time, maybe you want to use lock-free solutions, but that's not necessary just to support it. That's an optimization you could do later. And then you need to declare free threading support in your module init function. There's multiple ways of doing it depending on how you define your module init function, check the guide, and then specifically do not get rid of anything that mentions the GIL, anything that acquires the GIL, because those are very much still necessary, as I described before. And then you probably want to add some multi-threaded tests. And here's the fun thing about free threading. If you add multi-threading tests, if you have threading bugs, they will show up because you no longer have the GIL accidentally protecting you some of the time. So then let's talk about migrating Python code. That's going to be scary, right? Well, no, probably not. Probably you won't have to do anything. I mean, you probably won't have to do anything if you don't already have multi-threading bugs. The thing is, we don't make threads more complex by adding free threading. They were already complex. Existing bugs are more likely to show up, which is annoying, but it also means that just adding some simple tests will expose them that much quicker. So it's actually much easier to find those problems. Now, we're also making threading more attractive. So in the future, it's likely that people will use threads more. So that may also be a source of exposing bugs, right? Your code will be exposed to multi-threading more. And then to make your code scale well, where multiple threads are accessing individual objects, for instance, that may require very extensive changes. That's, even in Python code, that is not an immediately solved problem. Sharing objects between threads is still problematic for performance. There are ways around it. For instance, we have the ftutils package that we developed for some scalable containers, and then there's the Soreggi package as well by Daniela that contains even more of the same. Those are tools to use to create scaling multi-threaded Python code. So talking about the future, we still have work to do. We have ongoing performance and scalability improvements in the interpreter. We have the same in third-party packages that already support free threading. We also need to work on free threading support in third-party packages in general. We are doing well. I'm not saying this is necessary in order for free-threaded Python to be a success. It's already a success. It's already supported by more than half of the top packages with binary wheels on PyPI, which is really good. A lot of credit goes to Meta and Quansight, which we worked with to do not just the work, but also a lot of the work, but also education and convincing people and talking to people. And there are many other contributors involved. And then we have the future. Now, I'm on the steering council, and I'm not saying this with any authority whatsoever, but at some point, I expect free threading to be the default. Now, that doesn't mean much. That means when you build Python from source, you get Python by default. Or sorry, you get free-threaded Python by default. I expect we will be lagging behind downstream distributors like Red Hat and Debian, or large companies like Meta. We will be doing this after they have already done it, but it will happen at some point. And my prediction, again, with no authority whatsoever, it's probably not going to be Python 3.16, which would be next year. It's probably going to be before Python 3.20, and it's probably going to be this decade. And then eventually, once it's a default, we're going to make it the only option. We're going to get rid of the GIL build entirely. Now, what that's going to look like, what we're going to do with APIs, we don't know yet. This is far into the future. This is next decade. That's what I expect. But, I might be surprised. So that's my talk. Thank you for listening. I have some more cat pictures. So I mentioned in the booth, there's Meta. We're talking about Firefly, free threading, lazy imports, Cinder. We also have a Firefly workshop, and we have a free threading challenge if you want to try and create scalable code. So come talk to us, come see the challenge. And I think we have like 3 minutes for questions. Any questions? Be kind, Eric.
No, I have an interesting thing that you could have talked about that it relates to the nature of the contribution of Meta to this project. And I thought that's something kind of new in Python core development. And I think there are some great lessons that we've learned, the values and some of the challenges involved that you'd probably have some good insights to.
Well, that's a whole topic on its own. And it's a little complicated because I joined Meta after most of that work was done, right? It was Sam Groves, it was Carl Meyer, it was other people within Meta convincing Meta that this is something to invest in and convincing the core developers that this investment was something we should welcome. But I mean, that part didn't really need that much convincing. And then the management long-term didn't really involve me either, so I don't feel I'm the right person to really talk about those things. But yes, it's an interesting topic, and we should talk about similar projects more.
Thanks for the talk. You mentioned that you could enable free threading in a module by putting some code in the module. Does that imply that you can run code bases with both parts of it running in free threaded and other parts not?
Yes, I should have covered this in my talk itself. If you import something that declares that it supports free threading, then everything's good. If you import something in a free threading build that does not support free threading, then the GIL is re-enabled. It's not quite the same mechanism, but it's basically like stop the world, but we let one thread run. So you can still test everything, but you will get a notice that the GIL has been reactivated until you fix that extension module that causes it to be reactivated. There is an override. You can set enable GIL equals 0 to force it off, but that is playing with fire. So you probably only want to do that when testing. Larry.
I can answer why Larry Hastings abandoned the colectomy. In short, there were just unsolvable performance problems with reference counting, particularly crossing threads. I had a real trouble. I eventually gave up on destroying an object in the thread where the last reference died. I sent it back to the original thread that owned it. So I kind of had thread ownership of objects, kinda. And this cross-thread communication where we were sending objects and reference counts and things back and forth across the threads did not scale. The more threads you added, the worse that it got because it was contention for like the internal CPU bus that is clearing cache lines or something like that.
Yeah.
And so it was just dead stop. It just got worse and worse, and it was unsolvable. Sam Gross very kindly tells me that the techniques that he's using to manage reference counts in the no-GIL had not been invented at the time that I was doing the colectomy, and so I was really kind of, it was an impossible task at the time.
I will tell you, I seriously considered putting that anecdote in the talk, but I didn't want to make it sound like you weren't smart enough to invent that algorithm on your own.
Be fair. Oh, I lost it. Never mind. You interrupted
We're
me.
out of time anyway, so thank you, Larry. Like I said, come to the Python booth, come to the Meta booth if you want to talk more about free-threaded Python. Thank you.